So kindly put the heading and listen carefully. Beams with internal hinges. There is nothing extra you are going to study here. Again, the condition of equilibrium only. Okay, but the way you are applying should be little bit different. That means you should be a little bit careful so that you will be able to solve these questions. That's all. So put the heading and listen to me carefully. So once copying of the heading is over, please let me know. So after this concept, we'll see one more question on shear force diagram, bending moment diagram, and then we'll close this chapter. Okay, just to have enough number of questions for practice. Okay, so beams with internal hinges. So beams with internal hinges means here two beams are attached with internal hinge to produce another long beam. As we are using internal hinge, the way the beams will be bending will be a little bit different here. Look, so though we are assembling them into a single one, they have the freedom to rotate about that pin very easily. They have the freedom to rotate about that pin very easily. Understood? Clear? So, whenever you are dealing with a beam with internal hinge, following points should be taken care. Let's assume this point is B. First thing is, you neglect all the longitudinal forces, because longitudinal forces will not cause bending, so they will not cause any effect regarding bending moment diagram or shear force diagram. Okay, so if bending happens due to any load, then only effect of shear force will happen or effect in bending moment diagram will happen. Understand? But as the longitudinal loads will not be causing bending, so it's better to neglect them. That can reduce our calculation in solving the numericals. Okay, they will be of no use. So first step or first thing you have to keep in mind is neglect all longitudinal forces. Neglect all longitudinal forces. Understand? So in beams with no hinges, first of all, you have to keep in mind, you can neglect all the longitudinal forces. In fact, you can apply this thing for other case as well, because anywhere longitudinal forces will not cause any bending at all. But here, especially if you neglect them, it will be very helpful, because unnecessarily you think a statically determinate numerical as statically indeterminate numerical. So to avoid the confusion, I am asking you people to mandatorily follow this step. Okay? And second one, so whenever you are drawing a free body diagram, we should draw like this. I am assuming there is no load acting at this junction. So here they will be having mutual interactive forces. So let's apply, or let's assume reaction force from the right side beam onto the left side beam is By upside. So the reaction force due to the left side beam on the right side beam will be in opposite sense like this. So By both should add up to 0, because here net value is 0 here. Understand? For example, you have a load like this, something. So both should add up to this value. For example, you have a scenario where applied load is P here. I am just giving an example to make you understand. So at this location, external load is P. So what you should do is, you should apply like this. So out of P, some value, let's take it as K, is going onto this one here. So remaining parts, that is K minus P, sorry, P minus K, will go on to the second beam. So both should, that means effect of P is going on to both, so both addition should give you the value of P. So here there is nothing here, so both addition should give you 0. So By upside, By downside. Done? Coming to the third and very familiar one, as it is a hinge, moment about hinge is always 0. There is no restrictive moment. Understand? Anyways, from equilibrium condition also we can say that. So moment about any point, especially hinge equal to 0. So you can take moment about this point on the beam is equal to 0. You can take moment about this point on the right side beam is equal to 0. If you apply these conditions, you can solve easily the questions which are based on beams with internal hinges. So you can directly go into questions. So take the question from Mechanical Engineering 2005 gate paper and solve it and get the answer. So it's given that a beam is made up of two identical bars AB and BC. By hinging them together at B, the end A is built in cantilever and at the end C is simply supported. with the load P acting as shown, the bending moment at A. So here if you see that AB is a cantilever beam and they are expecting us to get the value of bending moment at the fixed support A. We know the first shortcut we studied. Bending moment at the fixed support of a cantilever beam is nothing but the reaction moment at the fixed support. So if you get the reaction moment at A, that itself is the magnitude of bending moment. Okay, we should use the shortcut, otherwise we will be doing extra one step. So if you draw the free body diagram for AB bar and BC bar, you will be getting the forces like this. So AB bar will be like this. So I told you to neglect longitudinal forces because they will not cause effect on bending moment diagram. So we have AY. So this we have BY. So B is the internal hinge. So here if you are taking B upside, so here you should take BY downside. And here we have the applied load as P. Here you should take CY. Again I am neglecting CX to follow the first condition. So these are the forces, and here reaction moment M naught will be there. So dimensions are L, this also L, this also L by 2. You should get the value of reaction moment M naught. If you apply the equations, sigma Fy is equal to 0. This gives you for this one Ay plus By is equal to 0, and applying sigma Mz is equal to 0, you will get, I am taking moment about this point, you can take about this point also, I am taking about this point. So M naught minus Ay into L, M naught is anti-clockwise, minus Ay into L is equal to 0. Coming to this, sigma Fy is equal to 0 means minus By minus P plus Cy is equal to 0. Taking moment, I am taking moment about this point, P into L by 2 clockwise, Cy into L anti-clockwise. So this gives you Cy is equal to P by 2. Cy is equal to P by 2. Substitute the value of Cy in this one, that is P by 2, minus P plus P by 2 minus P by 2, By is equal to minus P by 2. So if you substitute here, By is minus P by 2 means Ay is equal to plus P by 2, Ay is equal to plus P by 2 means M naught is equal to PL by 2. So this implies Ay is equal to plus P by 2, M naught is equal to PL by 2, which is nothing but bending moment at A. Okay? So this is the answer for this question. Clear? You can take this question as a homework because it is moreover similar to this question only. Very easy question. Or in this meantime, you can get the answer also. So we are done with this concept. Just like we have shear force diagram, which shows the variation of shear force along the length of the beam. Normal force diagram is which gives you the variation of normal force along the length of the beam. So we have already seen the normal force variation in first chapter questions only. Here also we can apply because in this example there is normal force variation along the length of the beam. So what we did was we took a shaft and multiple forces are acting. So let's say this is P1, this is P2, this is P3 and this is P4. Okay, so after doing calculation we understood that for this small a is there, for this small b is coming up, and for this one the value of normal force is small c. So we'll be getting those values. So simply along the length you plot the diagram. So normal force diagram, load P along the x. So here you will show the value of A. Understand? So from here to here you will show the value of B, and here to here you will show the value of C. So that is giving you the variation of normal force value along the length of the beam. Same way here also you can see. So normal force diagram helps you to find out variation of normal stress along the length of the beam. Understand? So you don't need to draw the diagram also because it's obvious from the diagram itself. I mean, you don't need to plot this graph also because from this diagram itself it is obvious the value of ABC. So wherever higher force to area ratio is there, that means higher stress is there. So in this question, they're expecting us to get the value of bending moment at the point R. Let me see the doubt of Ankit here. Yeah, okay. Ankit, I'll come to your doubt afterwards. So first of all, let me give the explanation for this. So in this one, if you take the whole beam, so I hope people have done the transferring of forces. So I'm taking only the vertical forces because they are causing bending. So at point Q, there is applied force of 10 Newton down, 10 kilonewton downside, and 10 kilonewton meter clockwise. And at R, so vertical force is 6 sine 30, so it is 3 kilonewton. So we'll be getting Py reaction force and Sy reaction force. Okay, so you can apply, you can get those values of Sy and Py by applying equilibrium condition. That's very easy. Now in this question they're expecting us to get the value of bending moment at the location R. At this location they're asking. Okay, so here you can eliminate many unnecessary steps, because if you have to draw the whole bending moment diagram, you should do cutting thrice. You should do cutting thrice. So left part of first cut, if you take the dimensions, so this is x-axis, this is 2 meter, this is another 2 meter, it is another 2 meter. So left part of first cut covers from 0 to 2, not including 2. Left part of second cut includes from 2 to 4, where 4 is not included. Left part of third cut includes 4 to 6. So 4 is included in the left part of the third cut. So we don't need to take these two calculations. We just have to take left part of third cut, because we are concerned about that point only. So if we take the left part of third cut, it is like this. There is a force of Py. You can calculate that. There is 10 kilonewton force and 10 kilonewton meter force. Okay, and there is 3 kilonewton force, and here bending moment m. So this is the distance of x, and these dimensions are 2 meter and 2 meter. Here if you go with this, you'll get the answer, but you'll be requiring little bit more amount of time, and there's a probability that you can do some mistake in taking the moments, because multiple forces are there and you can end up getting wrong answer. Instead, if you take the right part of the cuts, if you see the right part of the cuts, this becomes total 6 minus x. Here there's a force of Sy. Here anti-clockwise means here it should be clockwise. So if you take moment about this point, you'll get this value of m, which is nothing but this m only. Okay, and where x is, or the point x is equal to 4 is included in the range. So bending moment m is nothing but, so you can write down as m clockwise plus Sy into 6 minus x anti-clockwise is equal to 0. This implies m is equal to Sy into 6 minus x. You should substitute the value of Sy and you should substitute x value is equal to 4 meter. I think Sy is how much? 7 kilonewton or not? Okay, so yeah, Sanjay, that's the reason why I was explaining this thing. You should be recognizing that you can reduce your effort by taking the right side of this diagram. So thinking smartly is as much possible. Thinking smartly is very much important here. So if you solve it, you'll be getting the value of m, so which actually comes out to be 14 kilonewton meter, but our answer should be 14,000 Newton meter, because in this question they're expecting us to give the answer in Newton meter. Okay, you understood your unnecessary steps? So that's the reason why I made you to solve this question. So I hope you have understood the unnecessary steps. Clear? Let's come back to doubt by Ankit here. So Ankit is asking how to draw the variation of normal force diagram, or drawing of normal force diagram here. In this one, if you see the normal force values, I am drawing normal force values here. There is this beam like this. Due to hinge at P, there will be Px. At junction Q, there is no normal force. I mean, longitudinal force in other way, because 10 kilonewton will be giving rise to downward force and clockwise moment only. At junction R, 6 kilonewton is acting. 6 kilonewton is acting in a inclined direction. It is like this, so it will be having normal component or longitudinal component. It is nothing but 6 cos 30. 6 cos 30 is nothing but 6 sin 60, that is 6 root 3 by 2. It is nothing but 2 root 3. So at junction Q, junction R, we have the force as 6 Qx is equal to, Rx. Rx is equal to 6 cos 30, 6 root 3 by 2, it is 2 root 3. sorry, 3 root 3. Yeah, 3 root 3. So here we have the force 3 root 3 at this location, at the point R. It is acting exactly at point R. 3 root 3 kilonewton. And at junction S will not be having any force. So if you apply equilibrium condition, we will get, or you can apply net force and acceleration 0. So you will get Px minus 3 root 3 is equal to 0. So Px will come out to be again 3 root 3 kilonewton. This implies the member is like this. It is experiencing a force of 3 root 3 kilonewton here at this location, and at the location R, it is again experiencing 3 root 3 kilonewton. You apply this method which we did in the first chapter. You take this point as A, or anyway it is already given as P. This is R, this is S. You take it separately. So P, R and R, S. So I am doing the steps to avoid the confusion. Small a, small b, small b. At junction P we can say minus A is equal to 3 root 3. So A will become minus 3 root 3 kilonewton. At junction R we have B minus A is equal to 3 root 3. At junction S we have B is equal to 0. This implies B is equal to 0. So from this also we are getting A is equal to minus 3 root 3 kilonewton. So we got to know that from here to here there is a compressive force of 3 root 3 kilonewton, and from here to here there is no force at all in normal direction. Clear? I am rubbing this one to draw the normal force diagram. So this is normal force X. This point I am taking it as 0. This is 2. This is 4. This is 6. And this point is given as P. This is Q. This is R. This is S. So you understood that from P to R it is minus 3 root 3 kilonewton. So here the normal force diagram is minus 3 root 3 kilonewton from here to here, and all of a sudden from R to S it is equal to 0. So here 4 is, you can say that from here to here it is equal to 0. It is like this. So we see that normal stress in the member PQR is corresponding to 3 root 3 by area of cross section. It is compressive stress, and the normal stress in the member RS part is 0. So this completes our SFD BMD chapter. We will be going with the stresses in beams after this break. So you can see the summary. So we got slope of the bending moment diagram is equal to shear force magnitude. Slope of the shear force diagram is equal to load intensity. At the point of maximum bending moment shear force is 0, and at the point of maximum shear force bending moment need not to be 0. Okay. So please remember once again, conventional traditional method is as important as shortcuts. Okay, and again shortcuts are as important as conventional traditional method. Clear? So if we give a question and you see any of these 5 shortcuts is valid, you should use the shortcut mandatorily, otherwise you will be wasting your time, and the difference of time will come into hues. So instead of completing within 2 minutes, you will be completing within 20 minutes, so you will be wasting your time. Okay.